So let's go through these, um, this sort of question. It'll give you a little bit of practice with written because, like, I don't know, you don't get much practice with written. So it talks about a 4.5 kilogram greasy baby drops from a height of 12 meters onto a ramp, and at the end of the ramp there's a spring. The greasy baby slides into the spring and it compresses 50 centimeters, and the baby comes to a full stop for a moment before shooting back up. Okay, so the first question is asking, describe your system, open, closed, or isolated. So there's a couple options. So the first thing you have to do when I ask you a question like this is define your system. So we have our baby here, right? And if that is what we define as our system, well, here it's not moving, and then all of a sudden it's moving as it goes down here, so it looks like it's gaining energy, but the mass of the baby isn't changing. So if you define the baby as your system, then it would be a closed system. But if you want to define your system as everything in this picture here, well, we have potential turning to kinetic, turning to spring potential energy. None of the energy is leaving that box. So then it would be an isolated system, if that's what we're defining it as. Okay. So the second part, draw an energy bar graph for each of the following locations described, and that shows a relative value for energy. Okay. So we start off with the baby up here, and that's when it's got only potential energy because it's not moving, right? And we're going to keep our reference point at this line right here. So it's not quite at the reference point, so it still has potential energy, but now it's got kinetic energy, right? And then instant 3, the instant before the baby touches the spring, well, now it's at a reference point, so it's just going to have kinetic, right? And it hasn't touched the spring yet. And it's compressed 25 centimeters. So here, it's got spring potential, but it also has kinetic energy as well, right? And then after the spring is compressed 50 centimeters and the baby stops for a moment, well, now all our spring potential, all our energy is in spring potential energy. So if I wanted to draw this bar graph here, I would, for the first location, I would use 1, 2, 3, 4 boxes for my potential energy, because that's where what all that it has there. And as it moves down, it switches that potential into kinetic. So it's moved more than the halfway point. So I would probably say that it's probably got 1 bar-ish left of potential, and now it's got 3 bars of kinetic, like that. Right, so we want to keep those relative distances. If it was halfway to the ground, if it was at 6 meters, then I would say it would be 50-50, but it's probably 3 to 1, closer to a 3 to 1 ratio. Okay, and then at location 3, it's at a reference point, so it no longer has potential, and it hasn't touched the spring yet, so all 4 of those bars go into kinetic energy. Okay, and then it's compressed the spring halfway, so maybe half of our energy is in spring potential energy and half of our energy is in kinetic energy. And then the last location, it's gone all the way there, so all of our energy is in spring potential energy. So you can see that the total amount of energy or mechanical energy hasn't changed because it's always 4 bars, and we got to keep that consistent. But it's just switched forms as it's gone through the different locations. So this question says, determine the velocity of the baby at location 2. Okay. So at location 2, it's got, I'll bring this back here. At location 2, it has potential and kinetic. So we need a before and after. And I like to make my befores the ones that have the least amount of energy. So I'm going to make 1 my before and then 2 my after. So I'm going to use physics principle number 5, and I'm going to say all of my energy before equals all of my energy after. And before, I just have potential energy, and then after, I have potential, and I have kinetic energy. So remember that we can make these questions easier. I can move my reference point up to where the baby is at 2, and what that does is it gets rid of one of my potential energies. So now I just have kinetic, right? And we always measure that distance above our reference point, and it shows it's 8 meters above our reference point. So mgh equals 1/2 mv squared. Our mass cancels out, and move the 2 up top, and square root it, and we get 2gh is equal to v, just like we did in the practice questions. So it's going to be 2 times 9.81 meters per second squared, and we are 8 meters above our reference point, and we have to square root it. So 2 times 9.81 times 8, all square rooted. So the baby's going to be going 12 point, looks like we have 3 sigdigs in the question, 12.5 meters per second at location 2. Okay. The next question's asking us, what is the spring constant? So if I want to find the spring constant, I'm going to have to use location 4 or 5. And if I'm smart, I'm going to use location 5 because less energies to work with, less to rearrange. So I'm going to use location 5 as my after, and location 1 is my before, because all that energy sort of stays within our system there. So before, so physics principle number 5, energy before equals our energy after. So before I have potential again, and then after I have spring potential. I have 1/2 mv squared, oops, sorry, potential energy. I have mgh, and then I have 1/2 kx squared. Nothing cancels out, and I want to find that spring potential, or sorry, that spring constant. So I move my 2 up top, and then I move my x squared down below, and I won't screw this up this time to Mead. I will square that x. So I have 2 times my mass of my baby is 4.5 kilograms times 9.81 times my height. Sorry, I should write this out. 2 times 4.5 kilograms times 9.81 meters per second squared. And then my height. So now our reference point is back at the ground there. So we're 12 meters above our reference point here. And then it compresses it 1/2 meter. And I have to square that. So times 12 divided by 0.5 squared. And I get my spring constant to be 4.24 times 10 to the 3 newtons per meter. Okay. And then the third one says determine the speed of the baby at location 4. Okay. So we're just making this a little bit trickier. I'm going to leave that there. So I'm still going to use 1 as my before because it's a really easy before to use. But my after is going to be location 4 now. So at location 4 I have kinetic and I have spring potential energy. Okay. So I want to find my speed there. So the first thing I'm going to do is I'm going to move this to the other side by subtracting an EPS from both sides. And I should use my tick because it's after. So we have EP minus EPS is equal to my EK. I find it easier to do that first, rearrange it first, and then I'm going to try to find my velocity here. So it's mgh minus 1/2 kx squared is equal to 1/2 mv squared. Okay, we have a mass here, we have a mass here, but they don't cancel out because it needs to be in all 3. We have the 1/2 here, 1/2 here, but it doesn't cancel out because it needs to be in all 3. So what we should do is put brackets around this. That's why I like to rearrange it before. Move the 2 out in front, and move the mass down below, and then square root it. And that's how we'd find it. So we would go 4.5 kilograms times 9.81 meters per second squared. And we're still 12 meters above A at 4, so it's going to be 12 meters above our reference point to start, minus 1/2. We'll use our spring constant from before. I'll use my full number. So 4237.92 is my full answer. And then at location 4, it's only compressed 0.25 meters. Sorry, that might be off screen. Yeah, it's a little bit off screen. So you want to make sure that you square it. I squared it. There it is right there. And then we want to take this whole thing and times it by 2 and divide it by 4.5 kilograms and square root it. Okay, so I'm going to plug that into my calculator here so you can see it a little bit better. Oops. So in brackets, I'm going to go 4.5 times 9.81 times 12, close my brackets, and then subtract 1/2 times 4237.92, which is my spring constant, my full answer, and then multiply that by 0.25 squared, and then close my bracket. And then I want to multiply that by 2, divide it by 4.5, and then square root my answer, and I get my speed to be 13.3. So 13.3 meters per second is the correct answer. Okay. And then the last question. It asks, if the baby rebounds off the spring to a height of 5 meters, determine the energy lost as heat. Okay. So it only rebounds up to 5 meters above the ground. So I'm just going to, so I'll use this as my before, my spring potential energy, because there's still only one energy there. And then the baby goes up. This is my baby here. And my baby's only 5 meters off the ground. So here, it's got potential energy, but it looks like we lost some energy on the way up, and we lost it in the form of heat. So those would be my two types of energy. This would be my before, this would be my after. You can use EP, like location 1 is your before, it doesn't matter. But our energy before equals our energy after. So before, we have spring potential energy, and then after we have EP, and we have heat. So I'm going to subtract an EP from both sides. So I get EPS minus EP is equal to my heat. So that's how I would find my heat. So my EPS is going to be 1/2 kx squared. Oh, sorry, that was in the way the whole time. My bad. Ugh, my picture. Sorry, that's annoying for you watching it. This is still my little picture. There's it all written out. So 1/2 kx squared minus mgh equals our heat. Yeah. So 1/2, and I'll use that full answer again, 4237.92 newtons per meter for our spring constant. And then at location 5, it's fully compressed, so 0.5 meters squared. And then we subtract 4.5 kilograms times 9.81 times our height. We made it 5 meters off the ground for that last one. Sorry about that calculator being in the way. So if I plug all of this in, I can find my heat. So I want to go 1/2 times 4237.92 times 0.5 squared, close my bracket, and then subtract the 4.5 times 9.81 times the 5 meters off the ground. And that's how much energy I lose as heat. So 309 joules is how much energy I would have lost as heat. Okay, hopefully that helps. Hopefully go through it before and then check your answer with this and see if you get the right answer and see where you went wrong. So if you have any questions, feel free to email me or comment, and yeah, thanks.